Well, hello everyone. Let's try to continue the foundation engineering class on the estimation of settlement of shallow foundation. Okay, so today we are going to see how to consider the soil stiffness variation with stress level. How can we consider that in the estimation of settlement? Okay, as you know, when you load soil, it at the same time increase somehow the stiffness of the soil. Okay, when you're applying load, it means applying stress, right? So when the stress increases, it kind of like compacting the soil. So by doing that, you are somehow increasing the stiffness of the soil. So how does that affect the settlement of the shallow foundation? This is what we are going to discuss today to see how to estimate that. Okay, so if we check this figure, for example, I think in the chapter we didn't see it here, but it's the soil mechanics class, distribution of stress in the soil. If you go there, go back, you will see that when you load, depending on the shape of the load on the surface, there is a distribution of the stress in the ground, okay, according to the depth. So anyway, we suppose that here is your footing. When you load on it, you load the footing, you will have this kind of pressure bar inside. This is just your sand. So this is the influence zone caused, the influence zone of this load, okay? And the depth, the maximum depth it will reach is that this Z. GF is just the embedment of the footing, okay? So this Z is very important because it is allowing us to know which zone the load is going until which zone we can consider for the calculation of the settlement. Okay, so if the influence zone didn't reach here down here, so this means the soil down here will not be affected by settlement, will not settle. Okay, so this influence zone extend to depths sometime B, sometime between B and 2B. Okay, B is, as you know, even if it is not written here, it is just the width of the footing. So between B and 2B, 1 times the pile diameter in case of circular or pile width, or between 1 time twice the pile diameter according to this reference. Okay, so for square footing, square foundation, we will have this kind of approximately 1 time B. Okay, for strip footing, about this twice B. And for rectangular foundation, then we can do some kind of interpolation, okay? Logarithmic interpolation, yeah, between this one and this one, because strip foundation and rectangular, maybe they have same shape, except that the strip foundation, continuous foundation, the length of the foundation is large compared to the width. So this is what we can do, the logarithmic interpolation for in case of rectangular foundation. Okay, so L and B, you use the dimension of the footing. Okay, this L and B is limited to 10, 10. Okay, in the case of strip footing. So this means if you have L bar B higher than 10, then you might be in case of direct in the strip footing. Okay, you can see easily it here. If we replace this L bar B by 10, you can see that this will be 1, right? So 1 plus 1 is 2. So it means Z is twice 2B, and it will be similar to this now, strip footing. Okay, so it means before L bar B equal 10, your footing is still rectangular footing. Then after 10, it is strip footing. Yeah. Okay, so if we consider now elastic analysis, okay, we check the dimension of the foundation B and L, and we consider elastic body, okay. Then the settlement of our foundation can be estimated using this equation. So everything we will do in this lesson, today's lesson will be around this equation, How to obtain this SE, okay? How can we obtain this SE? Hmm. The settlement, okay? Elastic settlement. So as you know, this Q0 uh is it's here, okay? This load, yeah? The net applied pressure, okay? At this level, net applied pressure. B is the foundation width. ES is the modulus of elasticity, and we have seen several methods where how we can estimate this, okay? And the Poisson ratio, which is sometime around 0.3, okay, for sand. And this I is influence factor, which depend on the dimension of the footing. So we will try to find out how to estimate each of these parameters, okay? Yeah, we'll see. Sorry. So the Poisson ratio, okay, if we assume Poisson ratio to be 0.15 according to this reference, okay? Yeah, but Poisson ratio, don't be surprised to see it 0.3 in many cases. But if we assume 0.15 and the foundation to be rigid, and I think we did explain in this chapter what is rigid foundation, what is flexible foundation. So if we consider that this foundation is rigid, and then we can estimate this whole, this, which is in this equation, okay, using this figure, okay, and the H is the depth of compressible soil stratum. You can see H here, H divided by B. So for each value of H bar B, H is compressible soil stratum. So we can see the until the embed maybe the bedrock, okay, the soil here, the thickness of it is not written here, but the compressible soil stratum, and each value, for each value of H bar B, you can obtain the value of this group, okay, and each line here is representing type of foundation or dimension of foundation. So B divided by 1 by L, here 0, 1. It means the limit for strip footing, I think. Yeah. 0, 2, 0, 3 until 1. And 1 here means just square footing, because B divided by L like giving 1, it means they are same dimension. And that this one is for circular footing. Okay. So this is assuming this quotient ratio. Let me keep this equation here, the general equation. So application of the load to the foundation will increase the soil stiffness. So this is what I was saying. When you apply the load, the soil stiffness, because if the soil was like loose here, the stress will increase the stiffness of the soil. So this reference suggested that the modulus of elasticity can be written to consider that. Okay, you can see here this equation of the modulus of elasticity is now a function of stress. You can see stress here. We will see what is the meaning of each of these parameters. Okay, KE. KE is what we will call modulus number. The modulus number, no dimension for sand. And it depends on the relative density of the soil, strain level, like strain, some people mistaking strain and deformation. So strain level, and also the influence depth, this Z, this influence zone, the depth of this influence zone. So we will see how to estimate this K also, because as I said, everything will be around this equation here. Yeah, so we have to find each of the parameter. So starting with the modulus of elasticity, which can be obtained from this equation. So sigma prime 0 is the initial overburden pressure at the center of the influence zone. Okay, initially, the initial overburden pressure at the center of the influence zone, and the delta 1, delta sigma 0 is the vertical effective stress increase at the center of the influence zone due to the foundation load. Okay, so this one is before load, and this one is coming with the load, brought by the load. Okay, and this is atmospheric pressure. So if we have all these, we will be able to estimate the elastic modulus. So this means, according to this equation, this reference for a soil, you can easily estimate